Yeah, thank you. Good evening. So, so the agenda for today is to cover Bayesian learning and linear regression. If time permits, we'll also cover polynomial regression and the implementation aspects of linear regression and polynomial regression. So this is the agenda for today, right? So in the first session, we'll be discussing about the Bayesian learning. And then in the second section, linear regression. Linear regression is one of the very fundamental algorithm that any machine learning enthusiast, start with is learning. So don't miss out any of this. They are very important concepts. Great. So let's start with machine learning first. Excuse me. Excuse me. So let us start with Bayesian learning first. So in this session, we're going to discuss, we're just going to just review the Bayesian theorem that we have discussed in the previous class. Then we're going to discuss maximum a posteriori hypothesis and maximum likelihood hypothesis. And we are going to look at maximum a posteriori learners and then Bayes optimal classifier, naive Bayes classifier, and then Bayesian belief network. So these are the topics that we're going to cover in this session. Right. So why do we need Bayesian learning, first of all? So let us have a look at that. What are the advantages of Bayesian learning? Okay. So the Bayesian learning provides a probabilistic approach to the inference. So it provides some probabilistic approach. And it assumes that the things that we are interested to learn, the quantities that we are interested in, like for example the predicting the prediction values or the class label, that's what we are interested in, right? We are interested in estimating some value, either it is a class label or it is some continuous value. We are interested in estimating some value. So these quantities that we are interested to learn are governed by the probability distributions. So it assumes that the quantities of our interest are governed by some probability distribution, and the optimal decision can be taken by reasoning these probability distributions that we have together with the observed data. So it is important to the machine learning because it provides some quantitative approach to the to weight the evidence supporting alternative hypothesis. So it gives some probability. What is the probability that it belongs to certain class? So what is the probability that it is positive, or what is the probability that it is negative? So there is some quantitative approaches here. And also the Bayesian reasoning provides the basis for learning algorithms that directly manipulate the probabilities or indirectly manipulate the probabilities. So some of the algorithms directly manipulate the probabilities, like the Bayesian algorithms that we're going to discuss in this session. And some of the algorithms, they indirectly manipulate the probabilities. The example for this is the linear regression that we're going to see in the next section. Okay, so it provides the basis for both these kind of learning algorithms. Learning algorithms that directly manipulate the probabilities, learning algorithms that indirectly manipulate the probabilities. Though they do not explicitly manipulate the probabilities, the underlying concept is based on these probabilities. Right. So you're going to look at both the aspects one by one. So just to review in a different way, this is the Bayesian theorem, isn't it? So this is what we have seen in the previous class, isn't it? So in the previous class, we have seen what is Bayesian theorem. Probability of x given y is equivalent to probability of y given x times probability of x divided by probability of y. So this is what we have seen, right? Probability, I mean Bayesian theorem, right? So here I'm just writing it in a machine learning notations. Probability of hypothesis given data is equivalent to probability of data given hypothesis times probability of hypothesis divided by probability of data. So where probability of H is the initial probability that hypothesis H holds before even you observe the data. So even before you are observing the data, what is the probability that your hypothesis H holds? That is given by probability of H. This is a prior probability. So all these are the prior probabilities and this is the posterior probability. And probability of D is the prior probability of the training data. So irrespective of the hypothesis. So irrespective of, you do not have any idea or knowledge about the hypothesis. So irrespective of the hypothesis, what is the probability of your training data? That is given by probability of D. And probability of D given H is the probability of data given that hypothesis H is holding. So there is some world where the hypothesis H is holding. So there, what is the probability of this data, given data? So that is given by probability of D given H. And finally, probability of H given D, which is the posterior probability that we are interested to estimate. Probability of H given D, right? It reflects our confidence that H holds after we have seen the training data D. So this is what we are interested to compute, right? Probability of H given D we are interested to compute, which can be expressed as this using the Bayesian theorem. So if you observe here, probability of H given D is increasing along with probability of H and probability of D given H, whereas it is decreasing with probability of D. Right? If the probability of D increases, then probability of H given D increases. So what does that means? It means that the more probabilities that data will be observed independent of the hypothesis, the less evidence that the data is providing in support of that hypothesis. So I just repeat, it means that the more probabilities that the data will be observed independent of the hypothesis, the less evidence that the data is providing in support of this hypothesis. That is why as the probability of the data is increasing, probability of the hypothesis given data is decreasing, right? So this is the hypothesis, and how do you choose the best hypothesis is the question now. So this is how you express the hypothesis. And there is a world of hypothesis. There are many possibilities for the hypothesis. So all the possible hypotheses are expressed with a capital H. Right. So hold on for 2 minutes. You will understand with the example better. But try to understand this the Bayesian theorem and how are we computing the hypothesis? How are we selecting the hypothesis? For now, assume that there are many possible hypotheses and many possible hypotheses are denoted as capital H. So all the possible hypotheses are there in this capital H. Now, which one is the best hypothesis? There are many possible hypotheses. So which one is the best hypothesis is the question. Right? Can I say the hypothesis that maximizes the probability is the best hypothesis? Can I say that? Can I say that? Right?
Yes,
I
sir.
can say that, right? The probability, the hypothesis that maximizes the probability is the best hypothesis. So the maximum a posteriori hypothesis, selecting the hypothesis that is maximizing the probability of H given T. So for this data, what is the probability of the hypothesis given that data? So we compute this for each and every possible hypothesis. H belong to H. Okay, so if we expand this H given T and substitute this here, you would get this. Right, probability of D given H times probability of H divided by probability of D. And probability of D is same for all the hypotheses because it is independent of the hypothesis. Right, because it is same for every hypothesis, you need not consider that term in the denominator. Then this is equivalent to argmax of H belongs to H, probability of D given H, probability of H. So this is what the maximum a posteriori hypothesis is returning. which is returning a hypothesis that is maximizing this quantity probability of D given H times probability of H. Right. So if you simplify it further by making an assumption that each and every hypothesis is equiprobable. Right. So each and every hypothesis is equiprobable. It means probability of Hi is equivalent to probability of Hj for all Ij. Means what? Each and every hypothesis is equiprobable. So in that case, argmax of probability of D given H times probability of H is equivalent to argmax of probability of D given H. Because probability of H is same for every hypothesis. Right? So we call this as the maximum likelihood hypothesis. So this is a maximum a posteriori hypothesis and this is a maximum likelihood hypothesis. I want you to remember this maximum likelihood hypothesis, right? Because we're going to use this in the next session. Okay, so what it is saying, probability of H given D is equivalent to probability of D given H. So somebody is asking a question, what is argmax? Right. So argmax is an argument where X is maximized. For example, if you see here in the footnote, you can see here, right? Argmax f of X, X belongs to X. Okay. So it means the value of X that maximizes f of X. Suppose if you are writing argmax X f of X. So you're interested in finding X that maximizes f of X. So X is the argument of f of X. So you are interested in finding X that maximizes f of X. You're not interested in finding maximum f of X. You're interested in finding X corresponding to maximum f of X. Got it? So for example, if f of X is X square and X belongs to 1, 2, 3 and minus 3. 1, 2 and minus 3. So which X is maximizing X square among these three? Which X is maximizing X square among these three?
-3.
Minus 3. So it is returning an argument minus 3, argmax. So it is returning an argument that is maximizing a particular function. So here also, we're not interested in the maximum probability. We're interested in the hypothesis that is maximizing this probability. Right. So that is why we have given argmax here. Right. So this is how we choose the hypothesis. The hypothesis that maximizes the probability given data. Right? And according to the assumptions, this can be simplified as this or this. According to the maximum a posteriori hypothesis, this is simplified as this. And according to the maximum likelihood hypothesis, it is simplified as this. Right. So let us see an example for better understanding. Now we want to determine whether the patient have a cancer or not. So what information is given to us? This is the information given to us. Patient is taking a lab test and the result is coming back as positive. So patient took lab test and the result came back as positive. So the test returns a correct positive results in only 98% of the cases. Okay, it means what? If the patient has a cancer and the test results is also positive in only 98% of the cases. In remaining 2% of the cases, though the patient have the cancer, it is not predicting it as positive. It is predicting it as negative. So there is a 2% error in positive cases, right? So, and the correct negative results in only 97% of the cases in which the disease is not present. It means what? In 97% of the cases only, the test result is negative and patient also do not have cancer. Okay, and in remaining 3 cases, what is happening? 3% cases, what is happening? Even if the disease is not present, the test result is coming as positive. Right? So, and another information is also given to us, which is only 0.008 of the entire population have this cancer. So the probability of cancer is 0.008. So this is the information given to us. Now, with this information, what question it is asking? Does the patient have cancer or not? Given that patient takes a lab test and the result comes back to be positive. Right. So let us try to summarize the information given to us, first of all. So this is the information given to us. Probability of cancer is 0.008. So this is the information given here. Only 0.008 of the entire population have this cancer. So the probability of cancer is 0.008. So if we know what is the probability of cancer, can I get what is the probability of no cancer? Can I get that? Because probability of event plus probability of its negation is equal to 1. Right? So probability of cancer is equivalent to 1 minus probability of no cancer. And probability of no cancer is equivalent to 1 minus probability of cancer. So 1 minus 0.008 is equivalent to 0.992. I've got this. I can get this. Right? So another information given to us is probability of positive given cancer. Okay. So given that there is a cancer and the test also gives positive results in 98% of the cases. So probability of positive given cancer is 0.98. And from this, I can get probability of negative given cancer, which is 1 minus probability of positive given cancer, 1 minus 0.98, which is equivalent to 0.02. Another information given to us, probability of negative given no cancer is 0.97, and from which I can get probability of positive given no cancer, which is 1 minus 0.97. I got it as 0.03. Right. So this is the information given to us. So what are the possible hypotheses here? Possible classifications? Whether it's a cancer or not, positive or negative, right? So let us try to estimate the probability for each of the cases and see which is more probable. So probability of cancer given positive and probability of no cancer given positive, right? So we are given that the test results is positive. So that is why we are taking positive here. And we want to estimate whether the patient has a cancer or not, right? So we're trying to find the probability of cancer and probability of no cancer. So probability of cancer given positive can be written as this using the Bayesian theorem. Just now we have described the Bayesian theorem, right? Probability of A given B is probability of A given B is equivalent to probability of B given A times probability of A divided by probability of probability of B divided by probability of A. Sorry, let me write down.
Probability of B given probability of A.
Right. So using this formula, I can write probability of cancer given positive is equivalent to probability of positive given cancer times probability of cancer divided by probability of positive. Right. So what is the probability of positive given cancer? What is the probability of 0.98?
0.98.
I can substitute, right? 0.98 times 0.008 divided by 0.0376. We'll see that how we got this 0.0376, which is probability of positive. Right?
What is that 0.0376?
Sorry, ma'am?
What is that 0.0376? How you got that?
Yeah, we'll see that. That's what I'm saying. We'll see
Okay.
how to estimate that. But suppose if this is 0.0376, then this is the value that we got, 0.209. I'll explain how to compute that probability of positive. Right. So another possibility is probability of no cancer given positive, which is this, and this can be written as 0.03 times 0.992 divided by 0.0376, which is 0.791. So which label would you assign? Whether the patient has cancer or no cancer? According to this results.
No cancer.
No
No
cancer.
cancer, because no cancer is more probable. I'm very happy that many of you are responding. Thanks for that. So now the question is, how do we estimate the probability of positive? Probability of positive. What are the different ways that we can get positive results? One way is the patient is really having cancer and the result came back to be positive. This is one way. The patient is not having cancer, then what is, but still he got the results as the test results as a positive. So what is the probability that he is getting the positive in the case of cancer, and what is the probability that it is positive in the case of no cancer? So sum up them together, right? So probability of cancer is probability of cancer times probability of positive given cancer plus probability of no cancer times probability of positive given no cancer. Two possible ways, right? So both are possible, right? Because the test results is not accurate, right? So probability of cancer times probability of positive given cancer plus probability of no cancer times probability of positive given no cancer. So if you substitute these quantities, then you would get this 0.0376. That is how we got this 0.0376. Right? Yeah, yes, marginal probability. Right. Now, so that is how you can estimate the probability of cancer, probability of no cancer, and you are predicting it as the one with the more probable more probable hypothesis. Okay, so far we have sought that most probable hypothesis given the data D. Most probable hypothesis given D, which is maximum a posteriori hypothesis. So given a new instance, what is the most probable classification? Because the concept of hypothesis and concept of class is bit different, right? And maximum a posteriori hypothesis is not the most probable classification. It is the most probable hypothesis. Let us suppose, right? So to make things clear, let us take an example. Suppose there are three hypotheses, three possible hypotheses. Hypothesis H1, H2, and H3. And let's say probability of hypothesis H1 given D is 0.4 and probability of hypothesis H2 given D is 0.3 and probability of H3 given D is 0.3. So which is the most probable hypothesis in this case? Most probable hypothesis is H1, isn't it? They agree? H1, right?
Yeah.
And suppose if H1 classifying this instance, new instance X as positive, and H2 is classifying it as negative, and H3 is classifying it as negative, then which label would you assign according to the maximum a posteriori hypothesis? We assign positive label because it is H1 is the most probable hypothesis. Okay, but what is the most probable classification for X? In this case, most probable classification is negative because negative, the probability for negative is 0.3 plus 0.3, 0.6, whereas the probability for positive class is just 0.4, isn't it? So the most probable classification is different from the most probable hypothesis, right? The most probable hypothesis may not always give you the most probable classification, right? So taking all the hypotheses into account, the probability that X is positive is 0.4 and the probability that it is negative is 0.6. This is 0.6. And the most probable classification in this case is different from the classification generated by the maximum a posteriori hypothesis. Right. So what is that we have to do now? We have to take all the possible classifications for the new example, right? And then probability of Vj given D, that the correct classification for the new instance is, I mean, we have to just estimate what is the most probable classification from all the different values. Let's see how. So this is how you can assign a value to it. You're just taking the which is the most probable value, most probable classification for all the possible values of V. For that, what are you doing? You are taking the probability of each and every class over all the hypotheses here. So for Vj belongs to V, it means for all the possible values, you are computing the probability by summing up over all the possible hypotheses. Let's take an example for better understanding. Suppose the same example, probability of H1 is 0.4, H2 given D is 0.3, and H3 given D is 0.3. Right? And H1 is classifying the instance as a positive. So probability of positive given H1 is 1, and probability of negative given H1 is 0. And similarly, H2 is classifying the instance as negative. So probability of negative given H1 is 1 and probability of positive given H2 is 0. And similar is the case with H3. Okay, so now what are the possible values? How many values do we have? 2 values. What are they? What are the 2 values?
0 and 1.
0 and 1.
Positive and negative in this
Negative.
case. Yeah, right. So we have 2 values, positive and negative. So what is the probability for positive? You compute that using this, sum over all the hypotheses, right? Probability of Vj given Hi times probability of Hi given D. So 0.4 times 1 and 0.3 times 0, 0.3 times 0. So which is equivalent to 0.4, right? And similarly, if you take negative, this is 0.4 times 0, 0.3 times 1, 0.3 times 1, which is 0.6. Right. So we have got the probability of positive class is 0.4 and probability of negative class is 0.6. So which is more probable, negative or positive?
Negative.
Negative is more
Negative.
probable. So you assign a label negative to it. Right. Right. So this is how you can take best optimal classifier. Right. Next one is the naive-Bayes classifier. Naive-Bayes classifier is one of the very important and more practical classifier along with the decision trees, neural network, nearest neighbors. Right. So, but when to use it? We have multiple classifiers, no? Like I've mentioned, decision trees, nearest neighbors, all these are the different classifiers. So along with this is also one of the most practically used classifier, naive-Bayes classifier. But its use, when to use that is the question. When you have moderate or large training set available, when the attributes that describe the instances are conditionally independent given the classification. So these are the assumptions. The second one is the assumption. What is the assumption? The attributes are independent on one another given its classification. So we'll see what is that. And successful applications include diagnosis and classifying the text documents. So we'll see that. So here, what is the assumption? Assumption is that X is described with certain attributes. So your instance is described with a certain attribute, say 1 to AN, right? So moderate size, how many records? Okay, yeah, a moderate size is usually in thousands. Larger size is in lakhs. So yeah, where am I? So we assume that the target function X maps to V. It means X is the feature vector and V is the target value, right? So where each instance X is described with a set of attributes, and we are interested in most probable value of f of X, right? So we are interested in the value Vj that maximizes the probability of Vj given these attributes, right? It is same as this, same as previous. We are just taking a value that maximizes the probability of Vj given x, where x is the attribute set of attributes describing the instance, right? So x is a1 to an. If you expand x, it is because set of n attributes, if you substitute n attributes, you will get this. So you are assigning a value Vj which maximizes this quantity, probability of Vj given a1 to an. So if you expand this using the Bayesian theorem, you would get this probability of a1 to an given Vj times probability of Vj divided by probability of a1 to an. And probability of a1 to an is same because it is independent of Vj, right? So therefore, this is equivalent to, you can remove this denominator because it is same for all the values. You can ignore that, right? So therefore, it is equivalent to probability of a1 to an given Vj times probability of Vj. What is probability of Vj? Probability of that value, that class label, right? And what is probability of a1 to an given Vj? What is the probability that these attributes taking certain values, given the value, certain value for Vj, right? And because we are assuming that a1, a2, so on, an are conditional or independent of one another, given the value of Vj. That's what we have assumed, right? Right? Attributes that describe the instances are conditionally independent given the classification. Right? So given the classification, these are all independent. Because they are independent, there is an independent assumption. What is the independent assumption? What is probability of A comma B if A and B are independent?
Probability of A into probability of B.
Probability of A times probability of B.
B.
Right? And if I say probability of, what is the probability of A B given C? If I say that A and B are independent given C. If I say conditional independence, we call it as, what is the probability of AB given C? If I say A and B are independent given C. So this is equivalent to probability of A given C times probability of B given C.
B given C.
Right. So using the same rule, what we are saying here, probability of A1 to AN given Vj is equivalent to product over probability of AI given Vj. Right. So this is done using the conditional independent assumption. Right. So therefore, if you substitute this in place of this is equivalent to argmax of probability of Vj times product over probability of AI given Vj. We are assigning a label that maximizes this quantity. Right. There is a question in the chat box. When features have high covariance between each other, then we can use naive-Bayes classifiers. High covariance between each other, then there is a high probability. If there is a high covariance map, then usually we ignore one of them. In any case, either in this classifier or in another classifier. All right. So yeah. So this is the algorithm to summarize. Then we'll see with the example. So for each target value, we compute probability of Vj, and we also compute probability of Aj given Vj for all the attributes. So once we get these individual quantities, learning is complete. Only prediction is pending. What is the prediction? Prediction is the value that maximizes this. So just substitute the quantities that you have estimated in the learning phase and compute probability of each and every possible value and assign a label that maximizes this quantity. Right? Very simple. Let's take an example. So this is the example. This is the training data in which we have the instances described with the 4 attributes and we have one target value. So the problem here is whether the user buys computed or not. We have to predict that. What is given to us? We have given the user information, his age, his income, whether he is a student or not, here his credit rating. This is the information given to us. We should be able to tell whether he would buy computer or not. and we have given information about few training instances, right? These are the training instances. So given this training data and given a new instance for which we only know the person details, his age less than 30, his income is medium, the student, he is a student, and his credit rating is fair, right? So we have to tell whether he will buy computer or not, yes or no for this class level. So this is the problem, right? So what is the probability of yes here? Can anyone tell me? What is the probability of yes? What is the probability of no? Because if you see here, we have to estimate probability of Vj. Possible values. What are the possible values? Yes and no, right? So what is the probability of yes? How many instances are yes? And how many total instances? 1, 2, 3, 4.
9 by 4.
14, right? So 9 by 4. Am I right? 14?
Yes.
Okay. So what is the probability of S? Probability of S is 9 by
9 by 14.
14 and probability of no is 5 by 14.
5 by 14.
Okay. So we have got this estimate. Probability of Vj for both S and no. So what next? We have to estimate probability of AI given Vj for all possible values of Vj and for possible values of AI. Right? What are the possible attributes? Age, income, student, credit rating. So we have to estimate what is the probability of age less than 30 given S, right? What is the probability that age less than 30 given no? Sorry, 30 given no. Because for the new instance age less than 30. Right. Similarly, we have to estimate what is the probability that income is medium given S and what is the probability that income is medium given no, and so on, right? So let us estimate that probability of age less than or equal to 30 given Bayes computer equivalent to S, right? So given that Bayes computer equivalent to S, it means our search is limited to S instances. 1, 2, 3, 4, 5, 6, 7, 8, 9. So among these 9 instances, how many instances are with age less than 30? Among these 9 instances, how many instances are with age less than or equal to 30? How many of them are less than or equal to 30? So this is not, this is not,
2.
this is not. No.
2, 2.
1 and
2.
2. 2 instances are age less than or equal to 30 among 9 instances. What is the probability then? Probability is 2 by 9, 0.222. Right? And similarly, you can also compute probability of age less than or equal to 30 given Bayes computer equivalent to no. So we have 5 instances of no. How many are less than 30 among these 5? 1, 2, 3, 4, right? No, only 3. 3. Okay. So 3 out of 5. So the probability is 3 by 5. So we have done for this. What next? Income is medium. What is the probability that income is medium given Bayes computer equivalent to S? So this can be estimated in the same way. This is equivalent to 4 by 9 and Bayes computer equal to no 2 by 5 and so on. We have done for all the attributes in the target in the new instance, right? So we have got all the information required from this algorithm. We have got this probability of Vj and we have also got this probability of AI given Vj for all possible values of AI and Vj. So what next? We have to just substitute them in this formula for all the possible values of Vj and estimate the probability for each and every value, right? So let us do that. So what is the probability of X given Ci? X given Ci is this part, right? X given Ci. Ci is the class label. So multiply the individual probabilities. What are the possibilities for S? Attributes S. So this one 0.002, 0.444, 0.667, and another 0.667. This must be squared. 2 times it should occur. So this is equivalent to 0.004. And what is the probability of x given? Bayes computer equivalent to know. So this one 0.6 times 0.4 times 0.2 times 0.4, which is 0.019. So this part we have computed. This is done. So multiply it with the corresponding Vj and you would get the probability. Right. So probability that of S is equivalent to multiply this probability of X given Bayes computed equivalent to S with Bayes computed equivalent to S. So what is the probability of S? We have already computed, right? 9 by 14. And what is the probability of X given S, which is 0.444. So 0.044 times 9 by 14 is 0.028. And similarly, you can compute the probability of this no given x is equivalent to 0.019 times 5 by 14, which is 0.007. So to which class it belongs to? S or no? Which is more probable? S, right? S is more probable, right? So we'll assign a label S. I hope all of you have understood this example. Is this clear? Are you with me so far?
Yes, sir.
Okay, good. Okay, good. Thanks. So we said that we are assuming individual attributes are independent of one another given the class label. This is what we are assuming, right? Individual attributes are independent of one another given value of Vj. And because of that, we are getting this product over PAI Vj. Okay, but the condition of independent assumption is often violated in real-time datasets. Though we are assuming that all the attributes are independent of one another, they are not independent in general. Like Madam was saying, no, that there is a covariance between them. They're not completely independent of one another. If they're independent, covariance is 0. Right? So this assumption is often violated in case of real-time datasets. But surprisingly, this algorithm works well even if the assumption is violated. Why? Because the reason is the argmax value is same with and without that assumption. Okay, so this is the argmax value with the assumption. This is the argmax value without the assumption. Right? So though the values may not be same. So if you compute, let's say this is x and this is y. X may not be equivalent to y. Okay. So but the argmax value Vj that is producing x or y is same. Right? Did you get my point? So it means what? If the original value is 10, the estimated one is maybe 20. Or the other way, whatever it is. I'm just telling you some random example I'm giving. If the actual value is 20, this may be 30. If the actual value is 30, this may be 40. Right? But if you see where we have got maximum value in both the cases, here only, right? Isn't it? So the actual value may not be same, but the argmax value is same. That's what I'm trying to tell. So in most of the cases, that is why it works well, though assumption is failed. Okay. Yes, expression. So now another problem. This is one problem, right? Another problem is, what if none of the training instances with the target value Vj have the attribute value AI? None of the training instances with target value Vj have attribute value AI. Right? Let's suppose no one with age less than or equal to 30 has this value S in the target label. Then what would happen? The corresponding probability would be 0, isn't it? Probability of AI given Vj is equivalent to 0. So what happens if probability of AI given Vj is equivalent to 0? even for a single attribute. Even for a single attribute, if it is 0, what would happen? The whole quantity in the computation would be equivalent to 0, isn't it? Because it's a product term, isn't it? So this may lead to erroneous results. Because of a single attribute, the whole thing is becoming 0, right? So this may lead to erroneous results. So what is the solution for this? Solution is that instead of taking the actual probability, you estimate the probability. So if you compute the probability actually, it is NC by N, where NC is the number of examples for which V equal to Vj and A equal to Ai, and N is the total number of training examples. This is the actual value, actual probability. But now what are you doing? You are not considering this, because if NC is equivalent to 0, this thing would be 0 and the whole thing would become 0. So instead of taking this directly, what are we doing? We are adding something in the denominator and the numerator. So we are taking additional m examples and adding them in the denominator, additional m examples. And we know that prior probability estimation for that attribute. So using that prior probability estimation, we are just estimating the probability for this m instances. So prior probability estimate is taken into account. So through this process, the probability value will never become 0, right? Okay, but ma'am, what is this proba predict? Brinda ma'am. Probability prediction. Okay.
Predict the probability, sir.
Yes, ma'am. Yes, we are estimating the probability for each and every attribute, right? Right. So now I said the successful application of this naive Bayes algorithm is learning to classify a text, classifying the text document. Now the question coming is that why do we have to classify the text document? Okay, there are lots of applications for this. One application is learn which news article are of interest to a user, or learn to classify web pages by topic. So there are lots of application of classifying text. Okay, or that to which folder an email should belong to, that is also classifying text, right? Lots of applications. So naive Bayes is among the most effective algorithm for this classifying text documents, right? So now the question is, what are the attributes? Okay, so this is the best algorithm to classify the text documents. Then what are the attributes? How do you represent a document with a set of attributes? Is the question, right? So you can take each word position as a one attribute. So represent each document by vector of words and one attribute for word position in the document, right? So use the training examples to estimate probability of positive, probability of negative. Probability of positive means how many documents are of interest to user. Probability of negative means how many documents are of not interest to the user. And probability of document given positive, we have to estimate by taking product of probability of each and every individual word given that corresponding value. Okay, so using that conditional independent assumption, we are taking product over probability of AI is equivalent to WK given Vj. So what does this mean? What is the probability that word I is word WK is there in the word position AI? Okay, so given Vj. Okay, so if you are so strict about the word positions means a particular word must be there at a particular position. So you're considering, you're strict about the word positions. Suppose you have two classes, yes or no, and there are 100 word positions. It means 100 word positions in the document given, and all possible words are 50,000, let's say. So how many probabilities you have to store? How many probabilities? To compute probability of AI equivalent to WK given Vj. So Vj, yes or no? WK can be one of 500 words, 5,000, sorry, 50,000. And AI can be one of two. Right? So how many possible probabilities you have to store? 2 times 100 times 50,000, which is equivalent to 10 million, which is very big, right? To store 10 million probabilities you have to store, right? Suppose you are not strict about the word positions. It's okay. Wherever the word is coming in the document, you give the equal probability. I mean, the same probability for that, right? So you're not strict about the word positions. So then in that case, you're just interested in probability of Vj given W word I given Wj. So the possible values for this is 50,000. Sorry, yeah, 50,000. Possible values for this is 2. And how many probabilities you will have to store in this case? How many? 1 lakh. 2 times 50,000, that is 1 lakh. Okay, so the drastic reduce, right? So you are assuming that wherever it is appearing, you would give the same probability. Probability of A given WK is probability of AM equal to WK. Right? So with that assumption, you can reduce the number of probabilities that you need to store. Okay, so this is very simple. It is same as the naive Bayes. Only thing is that instead of attributes, you are taking words as the attributes. What is the probability of word 1? Suppose if you have 10 words, what is the probability of W1 given S? And times probability that W2 given S times probability of W3 given S, so on. Similarly, probability of W1 given no times probability of W2 given no, so same as the naive Bayes, rest of the things, right? So this is the algorithm. We collect all the words and other tokens that occur in the examples and we form the vocabulary. And for each target value, we estimate this probability of Vj and probability of W given Vj. Okay, once we estimate that, we just substitute that in the formula and give and compute which is more probable label, positive label or negative label. Right, this is how we can compute for classification. Probability of Vj times product over probability of AI given Vj. And this we have estimated in the previous algorithm in the learning phase. Right. Right. So that's all about the naive Bayes. We have seen one of the application also of naive Bayes, which is classifying the text documents. So any doubts so far? Any queries so far?
Excuse me, sir.
Yes, please.
Sir, earlier when there is an issue with naive Bayes, I mean, when there's a chance of probability becoming zero, so we have had some small correction, adding some m value and p value, right?
Yeah. Usually there are multiple ways to deal with it.
Yes,
Few
sir.
people just add +1 in the numerator if they do not have any idea about the prior probability estimate.
Yes. Yes, I
Okay.
mean, are those values, and suppose if we are adding some variable like m and all those, are they tunable in the sense when we are implementing it in the practical, is it in our hands to tune that also? Just like we give hyperparameter values and tune them, are they can we consider them as hyperparameters?
M value, no, it's not an hyperparameter. It's just you take the
It is a constant kind of thing.
sufficiently big number so that you ensure that
I
it
mean,
is.
we end users can give the values instead of the system takes it default. I mean, that's what I mean.
When you are implementing in from scratch, you have to define that.
Okay, sir. Yes, thank you, sir. Thank you, sir.
Yeah. Any other query? All right. So if no query, we'll move to the Bayesian belief network. Okay. So if you see this naive Bayes classifier that we have discussed just now, we are assuming that all the attributes are conditionally independent of one another, which we have also said that practically it is not the case. In real time, we don't have that, this assumption will fail. Okay, so the naive-Bayes assumption of the conditional independence is too much restrictive. But on the other hand, what happens if you do not assume this conditional independence? If you don't assume this conditional independence, it becomes intractable to deal with the problem. So what happens if you don't assume that? What is the probability of A1, A2, so on, AN given some value which? Right, you will have to deal with probability using chain rule. You have to consider all the probable possibilities, right? Probability of A1 given Vj, probability of A2 given A1 and Vj, probability of A3 given A1, A2, Vj, so on. Right? So if the n value is big, it becomes intractable to deal with this problem. You'll have to store so many possible probabilities. It is intractable to deal with all these probabilities if you have no assumption about these probabilities. And it is almost impossible to store all these probabilities and compute all these probabilities if the n value is big. N is the number of features in this case. Right? So if you don't assume anything, the problem becomes intractable. But if you assume something, it is too restrictive. So can we have something in between? We do not assume that all are independent. On the other hand, we do not also assume that all are dependent. We only say that some of the attributes are dependent on some of the other attributes. There is some conditional independence. So Bayesian belief network deals with that problem. The Bayesian belief network describes the conditional independence among the subset of the variables. So it allows combining the prior knowledge about the dependency or independency among the variables with the observed training data. We also call this as the Bayes nets. Let's see an example. But before that, we'll see the conditional independence. We have already seen this conditional independence. What is conditional independence? We say that X is conditionally independent of Y given Z if this condition satisfies. Probability of X given YZ is equivalent to probability of X given Z. What does it means? X is conditionally independent of Y given Z. So there is a condition. Given Z, it is conditionally independent of Y. Otherwise, it may be dependent. So given Z, X is conditionally independent of Y. So this can be expressed as probability of X comma Y given X given YZ is equivalent to probability of X given Z. So using this, we can say probability of xy comma z is equivalent to, in general, this is a formula, probability of x given yz times probability of y given z. Because probability of x given yz is equivalent to probability of x given z, you can write this way, probability of x given z times probability of y given z. So this is what we have got, right? In the previous slide also, one of the slides we have discussed this. Probability of xy given z is equivalent to probability of x given z times probability of y given z. So this is the conditional independence assumption. Okay, so now let's move to this example, Bayesian belief network. So this is the network that is representing or describing the conditional independence or dependence between the subset of the variables. So here we have some variables: storm, bus tour group, lightning, campfire, thunder, and forest fire. So these are the various attributes or the variables that describes the different things. Right. So this networks represent a set of conditional independent assertions, and each node is asserted to be conditionally independent of its non-descendants given its immediate predecessors. Right. Like for example, given lightning, this thunder is independent of all the other attributes. Right. Similarly, given the campfire, lightning, and storm, the forest fire is independent of the other attributes. So given its parents, one attribute or one variable is independent of the other attributes given its immediate predecessors, right? Given its parents, one variable is independent of the other variables. And this is the probability distribution at campfire. So campfire is this, right? This no. This is the probability distribution of the campfire, whether there is a campfire or not, according to the other values of its parents, right? So campfire, given that there is a storm and bus store group. Okay, storm is there, bus store group is also there. Storm is S, bus store group is also S. So in that case, probability that campfire is equivalent to 0.4. And probability of campfire given storm and no bus store group is 0.1. Probability of no storm and bus store group is 0.8. Probability of campfire given no storm, no bus store group is 0.2. And similarly, the other values. This is how we can interpret this probability distribution table at one node. Okay, so now if you want to represent the joint probability distribution over all the variables, joint probability distribution over all the variables. So if I say all the attributes are independent of one another, all the variables are independent of one another. Say, let's say I have three variables, A, B, C, and say four variables, A, B, C, D. If I say A, B, C, D are independent, then what is this probability? This is equivalent to probability of A times probability of B times probability of C times probability of D. Okay, so if I don't say that, then this would be equivalent to probability of A times probability of B given A times probability of C given AB times so on. Right. Now, with this partial independence or dependence, what would be this? This is equivalent to product of yi given parents of yi, because yi is only depending on its parents, not on any other variable, isn't it? So for I equal to 1 to n, this is equivalent to probability of yi given parents of yi. Right. So can you write that what is the joint probability distribution using this? Can you say? Anyone quickly? This is equivalent to probability of storm times probability of bus tour group times probability of lightning given storm times probability of campfire given storm and bus tour group times probability of thunder given lightning times probability of forest fire given the parents of forest fire. Right? So this is the joint probability distribution with this independence or dependence that is described in this graph. Have you got it? Are you with me? Are you with
Yes,
me
sir.
so far? Okay, cool, cool. So let's proceed. Any query, you can interrupt me at any point of time and ask. Right. So let's solve one example so that it will become more easier for you. So let's take, this is another example. There are four variables: pneumonia, smoking, temperature, cough. Four variables, and this is how, I mean, the probability distribution of the different variables given its weights. Okay, so probability of pneumonia is 0.1, probability of no pneumonia is 0.9, probability of smoking is 0.2. It means 20% of the entire population smokes, and probability of no smoking is 0.8. And this is probability of pneumonia given, probability of temperature given pneumonia is 0.9, probability of no temperature given pneumonia is 0.1. And similarly, probability of cough given pneumonia and smoking is 0.95. Right. So this is how you can interpret this probability distribution table. So now question, I have already told you this. I think. Okay, what is the probability of cough given smoking and pneumonia? Can you tell me? from the table?
0.95.
0.95. What is the probability of cough given smoking and no pneumonia?
0.6.
0.6. Yeah,
Six.
yeah, good. So this is how you can extract the values from this table. So now the question is, what is the probability of smoking given cough? So cough is given to us, right? So the patient is getting cough. What is the probability that he smokes from this distribution? Is the question now. So this is not directly there. This is not there from our observations. So what do we have to do? We have to estimate this from the given probabilities, isn't it? So what is the Bayesian theorem, Prashant, good. So we apply Bayesian theorem. Probability of smoking given cough is equivalent to probability of cough given smoking times probability of smoking divided by probability of cough. Right? So we can estimate this. Right? So we know what is the probability of cough given smoking? We do not know actually. Because there is another variable, pneumonia. We do not know that variable. We have to estimate it over all the possible values of pneumonia. We'll see that later. But what is the probability of smoking? What is the probability of smoking?
0.2.
0.2. Right. So this we know is direct. 0.2. So 0.2. We have to estimate the other. What is the probability of cough given smoking? Cough given smoking. So cough smoking. Cough smoking. Sorry. Right. Sorry. So cough smoking. Cough smoking. So what are the possible values for pneumonia in these two cases? Pneumonia true, pneumonia false. Okay, so estimate that probability of cough given smoking is probability of cough given smoking and pneumonia times probability of pneumonia. Because we do not know whether pneumonia is there or not. Pneumonia is there, then probability of pneumonia is equivalent to 1. Right? So because it is uncertain, we are just taking the probability of pneumonia also into account. And the other possibility is smoking and no pneumonia, which is this. Other one is this. Right? Times probability of no pneumonia. So if you substitute the values, you would get 0.127. And what is the other thing that you are interested in? Probability of cough. Probability of cough. So what are the possible values to get cough? Possible things to get cough? Either in both pneumonia and smoking, pneumonia, no smoking, no pneumonia, smoking, no pneumonia, no smoking. All the possible values are there, right? Isn't it? For the cough, you have all the possible values, right? For pneumonia and smoking, because nothing is given to you, isn't it? So take all the possibilities. Probability of cough given smoking and pneumonia times probability of pneumonia, probability of smoking, probability of pneumonia and no smoking, probability of no pneumonia and smoking, probability of no pneumonia, no smoking. All possible things, right? So this is equivalent to 0.227 if you substitute the things in that, right? So substitute all the things together. This would be equivalent to 0.127 divided by 0.227, which is equivalent to 0.56. This is the probability of smoking given cough, right? So have you got it? Are you with me following this?
Yes, sir.
Okay, sure. Another example. So this we have 4 variables: cloudy, sprinkler, rain, and wet grass. And this is the probability distribution table. This must be 0.9, I guess. Right. All right. So now what is the probability of curve? Joint probability. Probability of curve, rain, no sprinkler, and wet grass. How do you compute the joint probability distribution? Product over variable given its parents. So this is equivalent to probability of cloudy, because it doesn't have any parents. You just take probability of cloudy times probability of rainy given cloudy times probability of no sprinkler given cloudy times probability of wet grass given sprinkler and no sprinkler and rain. Right. So substitute, what is the probability? 0.5 times 0.8 times 0.9 times 0.9. So as I've told you, this is 0.9. Right. So this is how you can get the joint probability. Another question, quickly we'll solve. Suppose you observe that it is cloudy and raining. Cloudy and raining. Cloudy and raining. What is the probability that grass is wet? Wet grass is depending on what variables? What variables it is depending on?
Sprinkler.
Sprinkler and rain. And what is given to us among these two? Raining is given to us, right? It is said that it is raining, but we have no information about the sprinkler. Whether the sprinkler is on or not, we do not know, right? So we have to consider both the possibilities. So let us see that. So probability of wet grass given cloudy and rainy is equivalent to probability of rainy and sprinkler times probability of sprinkler given cloudy, because sprinkler is depending on the cloudy and cloudy is given to us. If the cloudy is also not given to us, we'll have to multiply this probability of C. But cloudy is given to us. He said that it is cloudy. It means probability of C is equivalent to 1. So you need not take this. So what is the other possibility for sprinkler? No sprinkler, isn't it? So probability of wet grass given rainy and no sprinkler times probability of no sprinkler given cloudy. Right. So if you do this, this would be, if you substitute the things required from the table, then this would be equivalent to 0.0909. 0.909. This is 0.9. All right. So this is how you can solve the problems. So two problems for you. You can take home and solve. Suppose you observe the sprinkler to be on and the grass is wet. What is the probability that it is raining? Suppose you observe that the grass is wet and it is raining. What is the probability that it is cloudy? This we can solve. So to summarize, learning of Bayesian networks, there are several variants of this learning task is there. Network structure might be known to you or unknown to you. And training example might provide values of all network variables or just some of the variables. If the structure is known and all the variables are observed, then it is easy. Just now we have seen the example. The structure is known to us and all the variables are observed. All the probability distributions are given to us, right? So this is a very easy case. It is easy to estimate the probabilities in this case. Suppose if the network structure is known, but some of the variables only observed, like for example, if this is not observed, then you have to estimate these variables such that the likelihood of this variable is maximized with respect to the other variables. So this is similar to learning hidden weights in the case of neural networks. Neural networks is not discussed with you, but yeah, it is similar to that. Right. So it is like learning some weights. If the network structure is known, but the variables are only partially observed, or all the variables are observed. If the network structure is also not known to you, from the data you will have to learn the network structure also by observing the variables, which variable is dependent on which variable is not dependent on which variable. All these things you have to learn from the networks, from the given data, which is hard problem. Right. So these are the different problems. Yeah, so this I have already told you. So that's all. If you have any queries, I'll take.
Yes, sir, I have a
Prasad.
question.
Yes, Prasad, sir.
Sir, in the last question that we solved,
Hmm.
we are assuming in case we do not know whether the sprinkler is on or off, and we are taking both the probability, both the cases. So how do we understand the tolerance of the probability that we have calculated, the range through which it can vary?
So this you're talking about this.
Yes.
So tell me, what is your question?
So in this case, we do not know if the sprinkler is on or not, and so we considered both the cases. So
Uh,
we have more multiplication in our calculation.
Hmm.
And so in that case, how do we know what is the tolerance plus minus, like how the data can vary, the probability can vary?
I didn't get what tolerance you're asking about, because we know the probability of sprinkler given cloudy, right?
Yes.
So what tolerance that you're asking? From that probability only we are estimating.
Okay.
So
Okay.
see, in order to have the wet cross, okay, so there are lots of possibilities. So these are the possibilities. If both sprinkler on and raining, then 0.99 chance that grass is wet. If the sprinkler is on but no rain, then 0.9 chance that grass is wet. If the sprinkler is not on, sprinkler is off, and there is a rain, 0.9 probability. If both are not there, sprinkler is not there, rain is there, only 0.01 probability. Okay, but what information is given to us now? The information given to us is rain is there. Okay, we are asking about what is the probability that wet cross. Right, but wet cross is depending on both sprinkler and rain. But we do not know what is the value of the sprinkler, isn't it? So to do that, what are we doing here? Two cases for rain to be true, this case and this case. If we consider these two cases, the sprinkler is true in one case, sprinkler is false in another case. Okay, so in both the cases, there is a possibility, right, to be wet cross, isn't it? So
Yes.
probability of wet grass given raining and sprinkler, less probability. Okay, no, I'll not take less now. Yeah. Another case is probability of wet grass given raining and no sprinkler. But we cannot directly take this because we do not know whether the sprinkler is on or not. So therefore, we have to consider what is the probability that sprinkler is on. Right? What is the probability that sprinkler is on? But the sprinkler is not independent. Sprinkler is depending on the cloudy, isn't it? So therefore, you also take sprinkler given cloudy, right? And times probability of cloudy. But here we are not taking this because it is already given that there is a cloudy. It means probability of cloudy is 1 because it is given to us. It is already said that it is cloudy. So therefore it is certain. It is not uncertain. So you remove this. You only consider probability of sprinkler given cloud. In this case also, we do not know whether it is a sprinkler or not. So there is an uncertainty. So take the corresponding probability. No sprinkler given cloud. Okay. So have you got this?
Yeah, my I was thinking in a way that if I predict the grass is wet, but let's say the sprinkler was not on in actual event, then the probability would vary to like in the range between 0.9 and 0.909.
No, it won't vary. The probability is set. I mean, you would get the same probability always with this assumption. It will not vary.
I mean, in when we use this on a larger scale and in neural network concepts, we would also be uh, talking about the tolerance or the error. I mean the accuracy of the model, and in that sense, I was thinking, but yeah, I get it now.
Okay, okay. Yeah, suppose if this is not observed, if this table is not present, okay, so you'll have to learn these probabilities also, right? So when you are learning these probabilities, you will be some objective at hand, that is maximizing the likelihood of that probability, that variable, maximizing the likelihood of that variable. So in that case, when you run the algorithm for multiple times, you may end up with a different probability distributions. Then you can consider the tolerance concept into account and can say that I can have maximum tolerance of this much. According to that, you can learn the probabilities. Got it? Have you got it?
Sir, is it termed as the EPOCH epochs? The number of times we run it to train or to understand the probabilities.
No, no, epochs is, I mean, yeah, how many times, how many iterations that you run this program, right?
Yeah.
Yeah, that is bit different. I'm just talking about, suppose you're talking about neural network, no? In the neural network, you are learning the hidden weights, isn't it?
Yes.
So suppose if this table is missing from here, okay, and suppose the problem is to learn the table also, then it is equivalent to learning the weights in the case of neural network.
Mhm.
Okay, so you will learn the weights such that the likelihood of that variable is maximized. So there is some objective. With respect to that objective, you will try to fill the quantities in the table. Okay, so now what I'm telling you is that like the way you are telling in the case of neural network, no, you have some tolerance. So in that case, you can also have a tolerance in this case also when you are learning this probability distribution, underlying probability distribution. But if the probability distribution is fixed, then there is no concept of tolerance. Every time you will get the same thing. All right.
Yeah. Thank you.
Right. So any other doubt?
Excuse me, sir.
Yeah, yes, Krishan.
Yeah, sir. Actually, I had small doubt, like in Bayesian and this Bayesian belief networks. I think what kind of parameters do we learn? Just in support vector machines or in other machine learning methods, we know we learn feature weights, which define our hypothesis function. I mean, or the curve which we learn. I mean,
Hmm.
that is we can imagine it as a black box function wherein we learn the weights, and when an unknown unlabeled data is given, with the
Hmm.
help of weights and data values, we'll predict the class level. I
Hmm.
mean, I'm unable to visualize for what kind of parameters or weights we learn in case of
Here
this
we are just
Bayesian operation.
learning the probabilities. You're just estimating the probabilities from the given data. So that's what we
Okay,
will see.
there is no parameter to be
No
learned.
parameter. It's a
Yes.
parameter-free method.
Okay. Okay. Sir. Thank you, sir.
Non-parametric method. We call it
Okay.
as a non-parametric.
Yes. Thank you, sir. Yeah.
All right. So if no queries, we'll take some 10 minutes break and come back. Is that fine? So the next concept is linear regression, which is very interesting. As any machine learning enthusiast, I mean, start with this linear regression model. Okay, so very interesting problem and very easy problem. So don't miss out. So we'll discuss that linear regression in the next section. So take a small break and come back by 6:35. Thank you very much. Yeah, I have not started. Yeah, give me 2 minutes. Just 2 minutes. Yeah, welcome back. Shall we start? Am I audible?
Yes, sir.
Yes, sir.
Yeah, thank you. So do you remember when we're discussing this types of machine learning, we have discussed the supervised learning, right? In that we said that there are two main types of supervised learning, regression and classification, right? So we're going to discuss regression. This is one of the very interesting topic to learn the concept of learning. Okay, so how does it learns? Okay, so let us see. I feel very excited to discuss this. So let us start this linear regression. So in this, we're going to discuss the problem formulation. What is regression problem? Then linear regression is one of the solution for this regression problem. We're going to discuss that. And optimization, different optimization techniques we're going to discuss. Gradient descent algorithm, mini batch gradient descent algorithm. Also, yeah, stochastic gradient descent algorithm. We also see vectorization of this problem. We also discuss the analytical solution for this, which is closed form solution. Some practical advices when you are implementing this. And finally, we'll also look at the probabilistic interpretation of the linear regression. Okay, so probabilistic interpretation, little tricky to understand. So don't worry if you don't understand it at the first glance. Okay, so slowly we'll observe, don't worry about it. So all right, so let's start. What is the problem? Okay, so the problem is very simple. We have given the training set of pairs x1, y1, x2, y2, so on, xn, yi, where xi is the future vector, d-dimensional future vector, and yi is the continuous target value. So continuous, you can observe this, right? The target value that we need to predict here is continuous, not discrete. So the task is to predict for the new instance xm plus j for j greater than or equal to. Right. So very simple. So I've given the information about the m instances. For m instances, you know the feature values and the corresponding target value. For m plus 1th instance, you only know the feature values. You do not know what is the target value. So you need to predict that target value. So this is the problem. Very simple problem. So let's start with an example for better understanding. So how do we predict housing prices? So we collect the data regarding the housing prices and how they related to size in square feet. Right. So let's take only one input variable, one feature, just for the simplicity, and then we will extend it to multiple input variables and multiple features. So each house is described by its size and price. So this information we have for the 10 instances. Given the 11th instance, how do you predict that house price? Right. So given this data, and a friend has a house of 750 square feet, how much can they be expected to get? Is the question. So this is the new house, your friend house, for which you only know the size of the house. You do not know what is the price. You have to estimate how much can they be expected to get. Audio is not clear. Okay, let's. Is it okay now? Is it better? Is my audio clear?
Yes, sir. Better.
Yeah. Okay. Okay then. Yeah. So this is the problem, and this is the data given to us. Suppose if I fit a straight line through the data, if I model this hypothesis as a straight line, right? So then how much can they be expected to get according to this model? So 750 means it is around somewhere $150,000, isn't it? Suppose if I fit a second order polynomial to the data, then it would be around $200,000, right? So before we're going to see what model that the linear regression is trying to fit to the data, we see the general recipe, machine learning recipe, right? So general procedure in the machine learning. So what is the machine learning recipe? So in machine learning, what we do is that with our training set defined, we give this training set to the learning algorithm. We give the training set to the learning algorithm. And learning algorithm gives us the hypothesis or a model or a function which summarizes the training data. Right? So given a training set to the learning algorithm is giving us the hypothesis or a model or a function which summarizes this data. And now, given a new instance, we give this new instance to this hypothesis or a model and gives us the estimated price. So which is a general machine learning recipe. We take the training set, we pass it into the learning algorithm outputs the function takes an input and estimates the value of y. General procedure. Now the question is, what is this hypothesis in case of linear regression? So how do we represent the hypothesis in case of linear regression? Because we said linear regression is one of the solutions for this regression problem. Right? Right. So how do we represent this hypothesis in case of linear regression? So in case of linear regression, we model the hypothesis as a linear combination of the input variables. So simply, we represent the hypothesis as a line in two-dimensional space or a hyperplane in case of multidimensional space. So what is the line equation? As you all know, line equation is ax plus b or mx plus c, whatever, isn't it? This is the line equation, isn't it? Isn't it the same as this? Theta naught plus theta 1x, where theta 1 equal to a and theta naught equal to b, isn't it? So we are representing the hypothesis as a line in case of linear regression, where theta naught and theta 1 are the parameters of this hypothesis. And a linear regression with one variable, we also call it as a univariate linear regression. Univariate because only one variable. That is why we're calling it as a univariate linear regression. If you have multiple variables, we call it as a multivariate linear regression. All right. So now the question is, we are representing the model or hypothesis as a line, and it means we are trying to fit a line to the data, trying to fit line or a hyperplane to the data. Now the question is, there are many lines that are going through this data. So all these lines are going through this data, and infinite number of lines may go through this data. So all these lines are going through this data, isn't it? So there are many lines going through this data. Which line is the best line? There are many lines that are going through this data. Which line is the best line? And what makes the line different? What makes the line different? Two parameters, theta naught and theta 1, isn't it? These two parameters makes the line different. And which is the best line? That line that minimizes the difference between the actual and the estimated prices. Can I say that? The line that minimizes the difference between the actual and the estimated prices is the best line, because you're at the end what you're interested in. You're interested in predicting the price of the house as close as possible to the actual value, isn't it? So the model that minimizes the difference between the actual and the estimated prices is the best model, and the model is line here, isn't it? So I say the line that minimizes the difference between the actual and the estimated prices is the best line. Would you agree with me? Agree with me?
Yes, sir.
Good. Right. So what is our objective? Our objective is to learn a line that minimizes the difference between the actual and the estimated prices. And what makes the line different? Two parameters, theta naught and theta 1, makes the line different. So therefore, what is our aim? Our aim is to learn the parameters theta naught and theta 1 such that the difference between the estimated price and the actual price is minimum. So we want to minimize the difference between the actual and the estimated prices. So we have to learn the parameters theta naught and theta 1 such that the difference between the actual and the estimated prices is minimized. So that is what our objective. So let's formulate our objective more clearly. Our objective is now very clear. Now our objective is very clear. So let us formulate our objective. So what is my estimated price? H theta of xi, which the model is giving. What is the actual price? Yi. Right. Because I want to minimize this for all the training instances, I've taken sum over equal to 1 to n and I've taken squared loss here. Okay, so to give more penalty to the instances where there is a larger difference, to give more weightage to the instances where there is a larger difference. And I just took average of them 1 by m. 1 by 2 is to simplify the mathematics in the future that you will understand in the coming slides. So isn't it my objective? Minimizing this is my objective, isn't it? Because I want to minimize the difference between the actual and the predicted. Actual is yi and predicted is h theta of xi. So my objective is minimizing j of theta. My objective is learning theta naught and theta 1 that minimizes j of theta. Right. So we want to minimize j of theta and we want to learn theta naught and theta 1 that minimizes this j of theta. So how do we achieve this? It's not that I'll chant some mantra om boom bush and select theta naught and theta 1 and that would be the optimal theta 1. I mean optimal theta naught and theta 1. It cannot happen that way, right? We have to start with some values for theta naught and theta 1 and gradually reach to the optimal values by searching these parameters in an optimal path. So how do we do that? So that is where the gradient descent helps us to learn the optimal parameters. Right. So now what is gradient descent? What is gradient first of all? What is gradient? So let us try to understand that from the very basic. Right. Prashant is saying it is slope. Yes, it is slope. Okay. So let us just review it. You may know it already. Let us try to review it. So let's take a very simple function, line. Line equation you take mx plus b. Okay. So if you see this simple line equation, what is m here? M is the slope or the gradient. B is value of y when x equal to 0 and x says how far you are along and y says how far you are up, all these things. And m is the slope or the gradient. So what is that it means? M is the slope or the gradient. It means what? As you vary one function, what is the slope of it? So as you vary x, what is the slope of y? As you vary x, what is the slope of y? So this is the slope. So that is you're getting through m. So how do you get m? Suppose I want to know what is the slope of this y as you vary x. How do you get it? So given this function y is given to you. So I am asking a question, what is the slope of y as you vary x? How do you get it? Suppose if I take the partial derivative of y with respect to x, derivative of y with respect to x. So what is this is equivalent to derivative of mx plus b respect to x. And this is equivalent to m. Am I getting it or not? I'm getting the slope, right?
Yes, sir.
When I take the, so if I want to know the slope of the function as you vary one variable with respect to some variable, it means as you vary one variable means with respect to some variable, you want to know the slope. Then what do? You take the partial derivative of that function with respect to that variable, you would like to know the slope. Suppose instead of x, it is a combination of, it is a function of multiple variables, x1, x2, so on, xn. Right, suppose if y is a function of multiple variables, m1 x1 plus m2 x2, so on, m3 x3 plus so on plus b. Suppose if you want to know the slope of the function as you vary x1, the slope of the function as you vary x2, and so on, then what do? You take the partial derivative with respect to each and every variable, and vector of all the partial derivatives together will give you the gradient. Did you get my point? So you take partial derivative of y with respect to x1, partial derivative of y with respect to x2, and so on. And the vector of all these partial derivatives together is giving you the gradient. So the gradient is just a vector of partial derivatives, a multidimensional space. So if the slope is positive, if the line is ascent, we call this as a positive slope. If the line is descent, then we call this as a negative slope. If the line is neutral or horizontal, we call this zero slope or neutral slope. Right? So now everything is good so far. We have got what is gradient. We have understood our objective. Now the question is how this gradient helps us to find the optimal parameters theta naught and theta 1. So that is the link. So let us try to understand that. So for that, let us try to represent a graphical, let us try to understand the graphical representation of the cost function. So the cost function j of theta that you want to minimize is looking something like this. So I've plotted this with respect to one parameter, but you can visualize it with respect to multiple parameters also later. Okay, so let's take one parameter for now, just for the simplicity. So the cost function that you want to minimize is something like this, and with respect to theta 1, this is one of the parameter. And where is it minimum? Where j of theta is minimum? Here, right? And for which value of theta 1 it is minimum? This one, isn't it? Correct? So for this theta 1, we are interested to learn, isn't it? So because this is the theta 1 that is minimizing the j of theta. So you're interested in learning this theta 1. Right? So suppose when you randomly initialize this theta 1, because I said you have to randomly initialize it first and gradually learn it, right? So when I randomly initialize this, there is a question in the chat box, I guess. So I'll come back to it after finishing this slide. Okay. So when I randomly initialize this theta 1, let's suppose the theta 1 is somewhere here. Okay. That means here j of theta is somewhere here. So what is the slope of the function here with respect to theta 1? Is it positive slope or negative slope? Is it a positive slope or a negative slope? It is a negative slope, isn't it? The slope of the function is negative here with respect to this theta 1, right? So what is the optimal value? It is here. So what am I supposed to do in order to reach to the optimal value? Should I increase theta 1 or decrease theta 1? Should I increase or decrease? In order to reach to the optimal value, I should increase the theta 1 value, right? This is when the slope is negative, right? Let's suppose when I randomly initialize, my theta 1 is somewhere here. And what is the slope of the function here? The slope of the function is positive. Okay, so the positive slope here and the optimal theta 1 is here. So what am I supposed to do here? Should I increase theta 1 or decrease theta 1? I should decrease theta 1 to reach to the optimal point. Right? So if the slope is negative, we have to increment theta 1 to reach to the minimum value of j of theta. And if the slope is positive, we have to decrement theta 1 to reach to the minimum value of theta, j of theta. So the gradient is guiding us to which direction we have to proceed. We have to proceed in the opposite direction of the gradient. If the gradient is negative, we have to increment. If the gradient is positive, we have to decrement. The gradient is guiding us to which direction we have to proceed to reach to the optimum value of c of theta. Right? So this is similar with respect to multiple variables also. Suppose if you have multiple parameters theta naught and theta 1, in three-dimensional space you can visualize this like a ball, and your objective is to reach to this optimal point where this is minimum, the bottom of the ball. Okay, so you have to adjust two parameters theta naught and theta 1 such that you would reach here the optimal value of j of theta. Right? So is this okay if I do this? I initialize theta naught and theta 1. and repeat this following procedure until convergence. What am I doing? I'm updating theta j values. Theta j equal to theta j minus alpha times derivative of j with respect to theta j. Okay, so forget about alpha for now. I'll tell you what it is later. So what is this derivative of j with respect to theta j? Isn't it the slope? Just now we have discussed, right? Isn't it the slope? Right. So it is a slope. So what am I supposed to do? If the slope is positive, I have to decrement theta j value. Let's see whether that is happening or not. So if this is positive, so what am I doing? Theta j equivalent to theta j minus some alpha constant times negative. So negative times negative, what is that? Positive. Means what? You are adding some quantity to this theta j when the slope is negative. Right? Similarly, if the slope is positive, what am I doing here? Theta j minus some positive value. It means I'm decrementing theta j. That is what I wanted to do, right? So when the gradient is negative, we are incrementing theta j, and when the gradient is positive, we are decrementing theta j. So when I am incrementing or decrementing, with what length I should increment or decrement is decided by this learning rate or step size. So what step should I take? Should I take longer step or should I take smaller step? Is decided by this alpha. If the alpha is small, you are taking small teeny steps. If the alpha is big, you are taking bigger steps when you are incrementing or decrementing theta j value. Got it? Right. So this is what you get when you take the derivative of j with respect to theta naught, and when you take derivative of j with respect to theta 1. So this I would want you to solve and see whether you're getting the same or not. Derive and see whether you're getting the same or not. Okay. So are you with me so far? Any queries? So this is very important.
Sir, alpha, how you will choose the value of alpha, sir? Suppose if we choose the minimal value.
I have a slide for that, ma'am. Brinda, ma'am, please
Okay.
hold on your horses for 5 more minutes. I have a slide for that. Any other query?
Equation changes, our assumption has changes as well. For example, in this curve, if the curve is different parabolic, then assumption changes as well. The function.
So you're saying that if the curve is like concave, or you're telling, yeah, then in that case, gradient ascent algorithm will work. This negative become positive.
Okay. And if the curve is too complex,
like non-convex, something like this.
Yeah.
Then the gradient descent may struck in some local optimum. So there are some other optimization algorithms, the meta heuristics or soft computing techniques, like particle swarm optimization. I'm not getting this word. And colony optimization. So different techniques to solve non-convex optimization problems.
Okay. Thank you.
Initializing to theta 1, theta naught. I mean, how do you initialize like
randomly, sir?
Randomly. So that should be taking random theta naught and theta 1 is like hyperplane in multidimensional point of view, right?
Yeah. Theta naught, theta 1 in hyperplane means you will have more than 2 parameters. Theta naught, theta 1,
theta 2, like that. Yeah. Okay, fine.
All right. If no doubts, we'll proceed to the next slide. Shall I?
Yes.
Yeah. Thanks. So this we call this as gradient descent approach, gradient descent algorithm, which is the optimization technique. So the gradient descent is an optimization algorithm used to find the values of parameters of a cost function that minimizes a cost value. And gradient descent is best used when the parameters cannot be calculated analytically using the closed form solution. Analytically means using the linear algebraic equation. If you cannot compute them directly, then this is the better way. We'll also see that one, how to compute them analytically in the coming slides. Don't worry about that. That's all about the univariate linear regression. Then multivariate linear regression. Suppose if you have multiple input variables. In the last example, if you see only one input variable, that is size of the house. Suppose if you have multiple input variables like, suppose if you take house price prediction example, size of the house, number of bedrooms, number of floors, age of the home, price of the house. So price of the house is the target value, but all these are the input variables. This is the output variable. Multiple input variables like more than one. Then we call this as a multivariate linear regression. So these are the some of the notations that we're going to use in the coming slides. N is the number of features, M is the number of examples, Xi is one instance, ith instance, one row. Okay, and Xij means jth column in the ith row, right? X32 means in the third row, second, this one. X32 is the number of bedrooms in the third house. So previously our hypothesis is theta naught plus theta 1x. So we have two parameters here, one variable x. Now we have multiple features x1, x2, x3, x4. So we have multiple parameters now, theta naught, theta 1, theta 2, theta 3, theta 4. So this is a hyperplane. So to generalize it, I have taken x naught equal to 1 and written this as theta naught x naught. Theta naught x naught, theta 1 x1, so on, theta 4 x4. If I take the vectorized notation of this can be written as theta transpose x. If I take theta as a column vector, theta naught, theta 1, so on, theta 4. And if I take x as also in column vector, one instance, if you have multiple instances, multiple columns, x naught, x1, so on, x4. Then what is theta transpose x? Theta naught x naught plus theta 1 x1 plus so on, theta 4 x4. Suppose if you just represent this theta as a row vector, you can just write it as a theta times x. Or if you take x as a row vectors, then in that case you can write it as x times theta. It all depends on how do you represent this, but this is how you can express this in a vectorized notation. Okay, so here also our cost function is same. We want to minimize the difference between the actual and the predicted, but only thing that is changing is h theta of xi. Earlier it is theta naught plus theta 1x. Now it is theta naught plus theta 1x1 plus theta 2x2 plus so on. Okay, and the gradient descent algorithm is also same. Theta j equal to theta j minus alpha times derivative of j with respect to theta j. Only thing that you need to remember is you have to simultaneously update all the theta j values. What do we mean by simultaneously updating theta j values? Is the question now. Okay, so listen carefully. What do we mean by updating theta j values? I'll tell you. So suppose you have multiple j values, theta naught, theta 1, theta 2, so on. Theta naught equal to theta naught minus something, whatever that you get here. Theta 1 equal to theta 1 minus something. Theta 2 equal to theta 2 minus something. Okay, so when you're updating this something, when you're computing this something, this may be a function of theta 1 or theta naught also. I mean, this must have theta naught also in this something. Okay, right, because it's a function of all theta naught to theta n. Right, now the question is, which theta naught would you consider? Would you consider the updated theta naught or this theta naught, the earlier theta naught? Is the question. Okay, so we have to consider theta naught from the previous iteration, not the updated one. That is what we mean when we say simultaneously update j values. When you simultaneously update, you do not have any information about the updated theta naught. Okay, so that's what it means when somebody said simultaneously update j values. So which parameter values you have to use in the updation rules? You have to use the parameter values from the previous iterations, not the updated ones. Similarly, here we have theta naught and theta 1 also. You shouldn't use this updated theta naught, theta 1. You should use the previous iterations theta naught, theta 1. Okay, so that's what it means simultaneously. That's what it means by simultaneously updating different theta j values. Got it? Any query here? Understood? Are you with me? So Uma Maheshwari. Yeah. Okay. Okay, you got it. Okay. Okay. So when n equal to 1, these are the rules. Theta naught equal to theta naught minus alpha times. This is the derivative of j with respect to theta naught, and this is the derivative of j with respect to theta 1. And if you generalize this equation with x naught equal to 1, this would be equivalent to theta naught, theta j equal to theta j minus alpha times derivative of j with respect to theta j. Right? And x naught j is equivalent to 1 for all the values of j. Right. Now, when you are implementing this gradient descent algorithm in practice, there are certain things that you need to understand. Okay, so let me discuss one by one. One is the feature scaling. Okay, so what is feature scaling and why do we require this? We'll understand that. So suppose if you take the example of house price prediction, the first feature is the size of the house, which may be in the range of some 0 to 2000 square feet. If you take the second house, which may be in the range of 1 to 5, it's not 0, maybe some 100 to 2000 feet, something like that. Okay. X2 is in the range of 1 to 5, number of bedrooms. Okay. So if you observe these two features, there is a huge range difference between these two features. Okay. So what happens if there is a huge range difference between the features? If there is a huge range difference, then the contours generated will be very tall and thin. So those who do not know what are the contour graphs, imagine this objective function that you want to minimize from the top angle. So if you see it from the top angle, what would you look at? You would look at like this, right? Isn't it? If you look at it from the top angle, you would see something like this. Yes or no? Right? And what is your objective? Your objective is to reach to this point, the center point. Correct? And anywhere you take this on one circle, the value of j is same, either here or here or here, because the height is same. Correct? So anywhere on one circle, the value of j is same. And your goal is to reach to this circle. So what happens if there is a huge range difference? If there is a huge range difference in the features, that will reflect in the parameters. So obviously there will be huge range difference in the parameters. As a result, this contour graph will not look like this. It will look like this, like ovals, thin and tall, something like this. Isn't it? So what is the problem? Earlier it is circles, now it is ovals. What is so problematic about this? You may think like that, right? But the problem is, because when you are updating one parameter, you are also using the other parameter in the updation rules, isn't it? So the second part in the updation, theta naught equal to theta naught minus the other one, right? So this part has theta 1 also. As there is a huge range difference, you may be incrementing or decrementing this theta 1 value more than required. Isn't it? Right? Possibility is there, right? So as a result, what is happening? Your path of reaching from the initial value to the actual, the destination value is zigzag. You are incrementing more than required and realizing, oh no, I have already incremented more than required. I have to go back. So going back, you're decrementing more than required and realizing that you have decremented more than required and incrementing it again, decrementing, decrementing, so on. So finally, your path is zigzag to reach to the optimal point. So there is a question, let me take that. The question here is that convex graph. Yes, sir, it is a convex graph. That is the assumption. Right. So yeah, so you may be decrementing or incrementing more than required. So what is the problem? If the path is zigzag, suppose you want to reach from village A to village B. There are two roads. One is this, road 1. The other one is road 2. assuming that other things are same, which one, I mean, traffic, road quality, all these things are same. Which road would you adapt? Road 2 or road 1? Will adapt for road 2 because it is the closest, right? You'll go fast, isn't it? Isn't it? So if you scale the features, then your contour graphs will be like circles and will be in the same range. As it is in the same range, your increment or decrement is not so big, right? So as a result, your path will be something like this and your gradient descent algorithm will converge fast. Okay, so running gradient descent on this kind of cost function can take a longer time to find the global minimum. Whereas if you do the feature scaling, it will bring the features into the similar scale. Therefore, the parameters also in the similar scale. And it means that gradient descent algorithm will converge more quickly. Right? So one of the things that you need to remember is scaling the features before you go for the implementation, model implementation. Right? So the second thing, there are various feature scaling methods. You can go through it. Max, mean normalization, Z-score. These are some of the popular scaling techniques. The second one, Brinda ma'am, your question. Learning rate alpha. You focus on the learning rate alpha. So how to choose alpha? You have to make sure that your gradient descent is working. When do you say that your gradient descent is working? If the cost is decreasing over the number of iterations, then you can say that your gradient descent is working, isn't it? Because your objective is to minimize the cost, right? So if the cost is decreasing, then probably you might have selected the correct alpha. If the gradient descent is working, then j of theta should decrease after each and every iteration. So you plot the number of iteration and versus j value, it should decrease something like this. Okay, so how do you check whether your gradient descent is working or not? Okay, I said you have to plot number of iterations versus j of theta, and when you plot, suppose if the curve is something like this, right? You have seen that your j of theta is increasing, means probably you need to select a smaller alpha value. Okay, so let me tell you one good example to make you realize that what is happening. Okay, so Manoj, our objective is to minimize the gap, right? What is the gap here? Manoj, can you speak up? I don't understand. Excuse me. Minimize the cost function. Probably you're talking about the graph. Yeah, we want to reach to the minimum value of that c of theta. Yes. So this linear regression model is not for the discrete. So there is a question from Brinda ma'am. I have discrete values in the data set. Do we need scaling? So this is not for the discrete data set. If you have a discrete features, then you have to convert them to numerical features. Then you can apply this. There are multiple ways of converting discrete values to numerical values. Yeah, Ravi Shankar. Yes, smaller alpha means it will take longer time to reach to the minimum. Yes. So let me explain you that. I'm coming to that point. Good. So I'll tell you a story. Forget about all this learning rate and everything. I'll tell you one good story to you. Imagine that there are two beautiful hills. There are two beautiful hills, and your house is located in between these two beautiful hills in a beautiful valley. You've got a very beautiful house in this beautiful valley. And imagine you're somewhere at one of the hills. Let's say that you have hills. This is one hill, and this is another hill, and this is a valley, and this is your house that you want to reach. Okay, imagine somewhere you are somewhere here. Okay, imagine you are a very big Rakshasa, like Kumbhakarna. Your feet is too long. Your foot is too big. Okay, so if you take one step, you're going from this hill to that hill. If you're taking another step, you're coming back from that hill to this hill. Okay, so with this step size, would you be able to reach to your home? You may be moving front and back between the two hills, but would you be able to reach your home? No, right? You'll not be able to reach your home, right? If you take two big steps, isn't it? Imagine you are a small ant. You have got teeny steps, small foot, teeny steps you are taking. Okay, so would you be able to reach home in that case? Teeny steps you will take, teeny steps, tin. Right? So yes, exactly. We'll reach definitely, but it takes very longer time to go to that point, go to your home. Right? So the point is, even if you take a bigger step, then it is you will not reach to the optimal point because if you are moving front and back, the value may be increasing. So maybe probably you have to reduce the alpha size. Okay, even if you take smaller alpha value, it takes very longer time to converge. Okay, so the point is you have to select the optimal alpha value. So this is one of the hyperparameters that you have to learn. Okay, you have to try multiple alpha values and see which is better in terms of time, in terms of accuracy, everything. Okay, and there are some line search algorithms, like they initially start with a bigger alpha, and as it comes close to the optimal point, they reduce the step size. So dynamically adjust the step size, line search algorithms, right? So there are various algorithms for that. You may go through them, right?
So thanks for the story. It was interesting. Visualize.
Okay, you're welcome. Thank you. Thanks. Happy to know that you liked it. All right. So let's go to the vectorized notation. So we can represent this uh, uh, features as a matrix like this, isn't it? And x naught is 1 because x naught is 1. You can add a vector of ones here, and this is the other features. So you can represent the whole thing as a vector, which is of size m by n plus 1, where m is the number of instances, n is the number of features, plus 1 because we have added vector of ones here. And this is why you can represent it as a column vector. Okay, so this is x, this is y. So what is our objective now? Our objective is to learn theta such that h is equivalent to x theta, isn't it? So our objective is to learn this theta naught to theta n such that h is equivalent to x theta. Okay, so in a vectorized notation, you can write our objective as this, because our objective is sum over 1 by 2m sum over h theta of xi minus yi whole square. Okay, so h theta minus y, h theta minus y. If you multiply, you will get h theta minus y whole square. Okay, so in vectorized notation, right? So you would get a single quantity here because you're taking just transpose and 1 by m times m by 1 single quantity you would get, right? So this is how you can write this in a vectorized notation. Similarly, you can express the updation rules also in a vectorized notation, like instead of updating each and every individual theta values like this, you can update all the vector at a shot, theta equal to theta minus alpha by m times x transpose x theta minus y. So now the question is, why do we need this vectorized notation? Why not simple individual updation rules? Theta naught equal to theta naught minus something. Why do we need this vectorized updation? Why do we are interested to updating whole theta at a shot, whole vector at a shot? Because it takes the advantages of the parallel architecture exist in the computer. So you can conduct this experiment. You one implementation, you write loops and update these theta values in a loop for I equal to 0 to n theta naught, theta I equal to theta I minus derivative of j with respect to theta j. In another program, you write in a vectorized notation. You will observe there is a lot of time difference, and vectorized updation is much more efficient than writing loops because it is taking the advantages of the parallelism exist in your computers. So that is the reason why we have to go for vectorization in the implementation part. Okay. So now let's discuss the closed form solution. This I was telling you, analytically solving for theta using linear algebraic equations. So far we have seen one way of solving for theta, which is the gradient descent algorithm. Now you're going for the second way of solving for theta, which is using the linear algebraic equations. Okay, so given x and y, our aim is to find theta such that y equal to x theta, isn't it? So our aim is to find theta such that y equal to x theta, isn't it? Right? So if y equal to x theta, can I multiply x inverse both the places? X inverse y is equivalent to x inverse times x times theta. And you know this formula, right? A inverse times A is equivalent to identity matrix. So this is equivalent to identity matrix minus times theta. And you also know the formula, right? Anything multiplied by identity matrix is equivalent to that. So using this is equivalent to theta. So I can write x inverse y is equivalent to theta. But what is the problem here? Problem here is x may not be an inversible matrix all the time. X may not be a inversible matrix all the time because this may not be a square matrix all the time. M is different, N is different. This is a rectangular matrix, right? So X may not be a inversible matrix all the time. So what to do now? So let's play a trick, right? So the trick is I take X inverse times I times Y because anything multiplied by I is equivalent to that, right? I take that as I. Now I can write using the inverse of this rule, I can write this as x inverse times x transpose inverse times x transpose. Right? Isn't it like A inverse times A? Yes or no? Where A is equal to x transpose. Right? So I substitute that. This is equivalent to theta. Okay. So now you all of you know the rule, right? AB whole inverse is equivalent to B inverse times A inverse. So isn't it in the same form? This one, B inverse times A inverse. Can I write it as a AB whole inverse? Using that, I write it as xt transpose x whole inverse times x transpose times y, which is equivalent to theta. Right? And x transpose x is always a square matrix. I hope you agree with me. Isn't it? X transpose x is always a square matrix. Agree? Right. So it is always inversible. This we call it as a pseudo inverse. So this way, just using this one equation, you can compute x transpose x whole inverse x transpose y. At a shot, you need not go for the gradient descent algorithm. Directly you can compute. So we got the solution in the second step, right? Why do we do the remaining? Uma Maheshwar, sir. So the problem here I have already explained. The problem is x inverse may not be an inversible matrix all the time because x is not a square matrix. So to solve that problem, we are going for all these steps and making that. Yeah. So x transpose x is always a square matrix. Therefore, it is inversible matrix. So therefore, you can do this. Now, one question may be running in your minds. If we get theta using simple equation, just like in a snap, Simple, very simple, right? X transpose X or inverse X transpose Y. Like a snap, you can get this theta. Why do we have to go for all that gradient calculations? Why do we have to repeat it over multiple number of iterations? Why to bother about alpha, theta, all these things? Okay, the problem here is inverse operation is costly. It is order of n cube. And if n is big, n means your number of instances. If n is big, what is the problem? If n is big, this order of n cube is taking lot of time. Okay, so the only problem is time, right? So when n is low, you can think of normal equations as the better option for calculating theta. And when n is big, gradient descent option is the better. Because this analytical equations take a longer time when n is big. Okay, so closed form solution work better when the input size is smaller and no need to choose alpha, no need to iterate. But if n is big, gradient descent algorithm is better, right? So we have seen one optimization technique, that is gradient descent. We also call this as a batch gradient descent or vanilla gradient descent. Vanilla means basic flavor, no? Right? That is why we call it as a vanilla gradient descent. So we also call this as a batch gradient descent, or vanilla gradient descent. Okay. So in this, to update a single value of theta j, we use the whole training set. We consider all the instances. So in this derivative of j with respect to theta j, we consider j with respect to all the instances, sum over I equal to 1 to m. Right? So we get all the instances. Right? Whereas in stochastic gradient descent, at a time, we consider only one instance, one example. Okay, and we iterate it over all the instances for I equal to 1 to m. Theta j equal to alpha times derivative of j with respect to theta j with respect to only single instance. Right? This is stochastic gradient descent. Mini batch gradient descent is in between these two extremes. Neither you are taking all the instances, nor you are taking only one instance. You are taking subset of the instances, mini batch of instances. You may divide the whole training data into 10 batches, and at a shot, you will take one batch, and you repeat this for 10 iterations. 10 times 10 mini batches you would consider. This is mini batch gradient descent algorithm. Okay, I forgot to mention one point, that I've told 1 by 2m is to simplify the mathematics, no? Right. So if you see this, j of theta, here we have taken 1 by 2m, right? So this is why we have taken, because when we take the derivative of this with respect to one parameter, this 2 will come this side. And 2 will get cancelled. To simplify that mathematics, we have taken 2 in the denominator, and adding 2 in the denominator will not affect our objective, because minimizing x is equivalent to minimizing x by 2. So using that theory, it will not affect our objective, and we are simplifying the mathematics. That is the reason why we have taken it 2 there, right? So that's all about the optimization. We have seen different optimization technique: batch gradient descent, stochastic gradient descent, mini batch gradient descent. We have seen, right? Now let us have a look at probabilistic interpretation of this linear regression. Okay, so I'm just cautioning you, if you do not get this, please don't get disappointed. Okay, so you'll absorb it slowly, don't worry about it. But the intuition, as long as you understand the intuition is what? You want to minimize the difference between the actual and the estimated prices. The intuition of the cost function. That is why we have taken the squared loss. But there is a theory behind it, why we have only taken squared loss, which is the theory based on the probabilistic interpretation. So when I was telling you this Bayesian learning, at the very beginning slide, I have mentioned that some algorithms explicitly manipulate the probabilities. Some learning algorithm, they do not explicitly manipulate the probabilities, but the underlying theory is based on the probability concepts. I mentioned that, no? So this is the example of that second one. It directly do not manipulate the probabilities, but the underlying theory is based on the probability concepts. Let's see how is it that doing that. Okay. So let us assume that y is generated by theta transpose x plus m. This theta transpose x is our x theta in our notations. So this is x theta plus m. It means that prediction plus some noise, isn't it? Because you may not always predict it correctly, right? Right. So there may be some noise in the y itself. Like for example, if your data is something like this, something is like this. Okay. So your h theta of x may be this, but there is some noise, right? It's not always correct, isn't it? So there is some noise associated with. So if you assume that this is a linear function, it means that there is some noise in the input itself. That's what you are assuming, right? So assume out that y is generated by theta transpose x plus m. It means there is some underlying function plus some random noise to it. So this is the underlying function h theta of x plus some random noise m. And also assume that m is the Gaussian noise with mean 0 and variance 1. Why is it Gaussian noise? Why is it this noise follows the normal distribution? Let us try to understand that. Mean 0 and variance 1. So just try to understand this. If you don't understand also, don't worry about it. It's okay. Right. So I'll try my best to explain this. So here, suppose this is the data. So imagine, so this is the data. Right. Okay. So this is the data. This is the value of your noise. Okay. So this is X and this is Y. Maybe your data is something like this. This data. Right. I'm just trying to represent that data. Right. So that data I'm trying to represent. And let's say this is your hypothesis, the underlying model from which this data is generated. Okay. So if you see this, data, you can see that you want this not, you want to fit this line or a function to be in such a way that for the most of the instances the error is 0. Agree? Imagine it like a 3-dimensional. Right. So this is the probability density of M. Probability density distribution for M. Okay. So what I'm trying to tell you is most of the instances are distributed around 0 mean. Mean is 0 here. Correct? Yes or no? So when you're trying to fit a line, you want it like for most of the instances, the error should be 0. And for very few instances, the error is high. And for moderate number of instances, the error is little low. Isn't it? So for most of the instances, you want the error to be 0. It means what? Your noise is following the Gaussian distribution. It's like for most of the instances, it is 0, and for very few instances, it is high. Okay, so you are assuming that your noise is following the Gaussian distribution. Right? So that is why we said M is the Gaussian noise with mean 0 and variance 1. Right? So if M is following the Gaussian distribution, right? So before that, let us try to reformulate the training data, because y is equivalent to h theta of x plus some noise m. So our training data is now become x1 comma x theta of xi minus m1. This is equivalent to y1, y1, and this is equivalent to y2, so on ym. Okay, where m1, m2 are the independent random variables. So m is a random variable representing the noise, and the noise is Gaussian. Okay, and we have got m number of random variables, and all of them are independent of one another, right? Because you have got m instances, right? So the Gaussian random variable z with mean mu and variance sigma square has this probability density function. This we have seen in the previous class, isn't it? Yesterday's class we have seen, right? The Gaussian distribution follows this probability density function. Gaussian random variable follows this probability density function, probability distribution function, right? So using this, what is this for m? Because m is 0 mean and variance 1. So mu is 0 and sigma is 1. Sigma square is 1, therefore sigma is equivalent to 1. Okay, so if you substitute those values in this, what would you get? This is equivalent to 1 by 2 root of pi e minus m square by 2. Z is equivalent to m, isn't it? So this is what you would get, right? Following me? Or lost? Following me? Yes, good. Good. So yeah, so we are assuming this. Yeah, Mohammed said variance is 1 because we assume it to be a constant variance. It's not that it is varying for each and every instance. Yeah. So yeah, so this is for m. And similarly, equivalently, you can assume that probability density function with respect to y is 1 by square root of 2 pi e power minus y minus s theta of x. Right? Because m is equivalent to, because m is from this, you can write m is equivalent to y minus h theta of x. Okay, so you can write this m in place of m, you can write pi minus h theta of x all square. Right. So now what is the, so this is all fine. So this is what your probability distribution is. And this is how the instances are distributed. Right. So now what is the matter? What is the value of theta? We want to select theta that maximizes the likelihood, isn't it? So we always want to select, we always want to select the data that maximizes the likelihood. Always want to select, parameters, theta that maximizes the likelihood of data, isn't it? So we want to select theta that maximizes the likelihood, probability of theta given theta. So this is the probability and this is the probability function, and we want to select theta that maximizes this. We want to select theta that maximizes this. Agree with me? Agree with me? Isn't it? So this is the probability and we want to select theta that maximizes this probability given data. So do you remember, according to the maximum likelihood, if you expand this, this would be equivalent to maximize theta. This would be equivalent to what? Probability of d given theta times probability of theta divided by probability of d. Because probability of d is same for all, you can ignore this. And if you assume in maximum likelihood, you are assuming every hypothesis is equally probable, therefore you ignore this. So you are interested in finding this maximization of theta with f of d given theta. So that's what I have told you, in the previous section. Remember this, you will use this, right? So there is a beautiful connection between whatever that you have learned and here. So I just want you to realize that. If you realize, you will appreciate. Otherwise, you will not appreciate, right? So you want to maximize f of t given theta. So f of theta given d is equivalent to f of d given theta. Right. So that is why you are doing this. F of d given theta. Right. And you know that all the individual instances are independent of one another. That's what we have said in the previous slide. Okay. So using this independent assumption, you can take the final probability as the probability of the individual instances. Okay. So you know that all the variables follows this Gaussian distribution. And if you substitute them in the formula, you would get that 1 by square root of, 1 by square root of 2 pi times e power minus ya minus h theta of xi whole square by 2. Because all of them are independent, you are taking product over here. Got it? Is it clear so far?
Yes, sir.
Yeah. So now maximizing something, maximizing some x, let's say not x because we are using this x. Let's say maximizing some a is equivalent to maximizing log of a. Agree with me? Agree? Maximizing a is equivalent to maximizing log of a, isn't it? So take log both the sides, log of f of d equal to this, and you know that log ab is equivalent to log a plus log b. Got it? So this is the formula we have, right? So product over becoming sum over. And this is a constant term which is coming here, log 1 by 2 pi minus sum over equal to 1 to m ya minus h theta of xi. And log and e gets cancelled. That is why we have got this here. And because this is a constant term, you can ignore this. And what you are interested in? You are interested in maximizing this. And maximizing a by 2 is equivalent to maximizing a. So therefore, you are interested in maximizing this. Theta that maximizes this. Minus, sorry, this one. Minus of max of sum over I equal to 1 to m yi minus h theta of xi whole square. So this is your objective. So maximizing minus a is equivalent to minimizing a, isn't it? Agree with me? Maximizing minus a is equivalent to minimizing a.
Yes,
So
sir.
maximizing minus of this is equivalent to minimizing sum over equal to 1 to n yi minus h theta of xi whole square. So now tell me, have you got your objective? Isn't it your objective? yi
Yes, sir.
minus h theta of xi whole square? Yeah, so that is the beauty of it. You have got this from this probability distribution assumptions. Okay, so if you realize this, you will really appreciate this. So there is a question. It is about equivalence between, yes. Right. Now the question is, who cares about this probabilistic interpretation? Why is it important? I've understood the difference between, the intuition that I want to minimize the difference between that actual and predicted. So therefore, I'm taking squared loss. That is clear intuition. Why should I care about this probabilistic interpretation? Because this squared loss you have got based on some assumptions. Assumptions are what? Assumption is noise is additive, first of all, first assumption. And noise on each observation is independent and identically distributed. That is why you're taking product over here. And noise is Gaussian. These are all the assumptions that we have made and ended up with a squared loss. Suppose your assumption is changing. Suppose you know that your data is not following this assumption and your data has got different assumptions. And based on that, suppose if it is not Gaussian noise, some other noise, then you may end up with a different cost function, isn't it? So the changing the loss noise model would lead to a different loss function. So that is why you need to care about that. And we can also leverage the wealth of the results and approaches from the probability statistics and perhaps gain a new insights. For example, in linear regression, without regularization, our estimation of theta is the maximum likelihood estimation. So this enriches our results and approaches from the probability and statistics. That is why you need to care about. So that's all. If you have any queries, quickly we'll go to the implementation part and wind up. Any query?
Excuse me, sir. Sir, while we had different gradient descent approaches implementation, like batch gradient descent as well as normal and this stochastic gradient.
Stochastic
Yes, sir.
mini batch.
So, but yeah, they seem to be same. I mean, there is a computational cost difference, but are we sure that, I mean, both have same equivalent results, in the sense we get same result, same set of parameters, even as a result, even if we go for batch or stochastic gradient, when is a result parameter is same, if your starting initial random starting point is same, and remaining all conditions are same, are we sure that both give a same resultant
See,
value?
when you are taking average of all the instances, it means in case of batch gradient descent, you're considering all the instances, right?
Yes, sir.
So it means that it may not be varying that much. Like
Okay.
if you see the graph, something like this, you may get something, I mean, there may be, though there is some little distractions like this, but most of the time the glass is constantly decreasing. But
Okay.
if you update based on a single instance can be any extreme, isn't it? Because it is not taken average, so the variance may be there in the, which you consider with respect to single instance. So
Yes, sir.
sometimes it may be increasing, sometimes it may be decreasing. So your graph will be something like this. Mini batch gradient descent is in between these two. Okay, so yeah, you may end up with similar results, not the same results, but the
Yeah.
time that definitely different.
Yes. Yes. Thank you, sir. Yeah.
Any other query? All right. So I thought of actually going through each and every step of, working out each and every step, something like this. I've given dash to fill out, but then now the time is only 10 minutes left. And even if I go through the whole code, it takes around 20-30 minutes. So I choose not to do this. Instead, I think I have another file where I have filled out this. Let me find out that so that we can go through the code and understand it. Yeah, it is filled there. Okay, let me take this. So the first step is to import the packages that are required. Okay, so these are all the different packages that I require. I'm just importing them. NumPy, it might have been covered in your Python class, right? So NumPy is to do all vectorized numerical computations. So I'm just importing NumPy, import NumPy as NP. And I'm also importing sklearn.datasets. So this is a library, very important library for machine learning. Remember sklearn, scikit-learn. Scikit-learn library, we have almost all the machine learning implementation, function, model implementations, both from the supervised and unsupervised learning. Reinforcement learning, this package doesn't have. Another packages we have. Right, that will be demonstrated in the classes, reinforcement learning anyhow. So the scikit-learn library is very important. So in this we have data sets, we have models, we have pre-processing techniques, everything is there in the scikit-learn library. So for data sets, you have sklearn.datasets. I'm importing Boston dataset, which is the Boston house price prediction dataset. Right? So load Boston is the method from which I can get the dataset. And I'm also importing matplotlib for better understanding of the problem at hand with some visual aid. And I'm also importing sklearn.model selection. From that, I'm importing train test split. Train test split is to divide the data into training and testing and build a model on the training data and evaluate the accuracy on the test data. So this is the train test split that I'm importing from sklearn.model selection. So these are all the packages that I require. And next thing is loading the data set. So the point is I'm just trying to develop the individual functions required and then finally integrating them or integrating all of them. So load data set function, which loads the data set and bring the data set in the required format. So I'm loading the data set by calling this load Boston, which I have imported here, load Boston, right? So I've load Boston imported, and this is the data set. It is loaded into the data set. Now, if I access this data set using data, it will return X to me. And if I access this using target, then I will return Y. This np.new access is to make this as a column vector, right? So to match with the notations, right? So X and Y I've got, I'm just returning them here. So this is the functionality of this function. The next one is computing the cost. So this is the cost function that we have, right? 1 by 2m sum over equal to 1 to m h theta of xi minus y. And you know h theta is x theta, right? So just compute that. What are the input parameters required? X, y, and theta. And m also we require. M is the length of the data set, number of instances in the data set. You can use length function to find out the length of y. So y is the column vector, right? The length of y can be, you can get it from len function call by. And to take the dot product of two matrices, a matrix and a vector, you can use symbol. Or equivalently, you can use np.dot function. From NumPy library, you have a dot function which takes the dot product of two matrices that you have passed to that function. Okay, you can use either of them. Is very simple, so I've used that. X theta means it is computing this h value, this one, x times theta. Right. So once you get that, what is your job? You have to find out x minus h minus y. So h minus y and star 2 means square of this. So element y square, because this h is a vector, y is also a vector. Vector of all the predictions and vector of all the actual values. So it takes element y square and then takes sum over that all the individual squares np.sum and multiply it with 1 by 2m. Right? So this is computation of the cost. The next one is gradient descent implementation. This I am explaining it to you from the scratch, but you can directly compute using the library. That also I will show you. Right. So the gradient descent updation, this is the rule that I have got it from the slides, theta equal to theta minus alpha by m times x transpose x theta minus y. Right. So this is a gradient descent algorithm. Initially, all j values are assigned to zeros. Okay. So j history is to capture the j value over number of iterations. What is the j value at iteration 1, iteration 2, and so on. So I'm just making it as zeros of size and number of iterations by 1. Right. So theta equal to theta minus, I'm writing that this rule, theta equal to theta minus alpha by m. X dot t means x transpose. X dot t means x transpose, and at the rate is for dot product for the multiplication. And x at the rate theta means x times theta minus y. Right? And I'm just storing this compute cost, the j history of y. This I'm repeating it for the number of iterations. Just returning j history and theta. And this is the normalization. I've told no, we have to normalize the features. You have to scale the features. I have used mean normalization, which is subtracting mean from each and every element and divided by the standard deviation. So for this, I have to compute the mean. Mean is computed by calling np.mean from NumPy library. I'm calling mean, and mean is computed column wise. That's what it means, 0. If I give 1, it computes mean row wise. Right. So column wise mean is computed, column wise standard deviation is computed, and all the columns are updated at a short with this normalized value, x equal to x minus mu by sigma, and returning this normalized x. Right. So I hope my screen is very clear to you. Is it? Yeah, all right. And this is the mean absolute error, which is the absolute difference between the actual and the predicted. I just implemented, but this also there in sklearn.metrics. That also I will show you. So now I've got all the things that I required. So I'm just implementing the linear regression model by taking x and y. Number of iterations I'm initializing, learning rate alpha I'm initializing, number of samples, number of features, everything I'm computing, and theta I've initialized to zeros, but you can randomly initialize. Random initialization is better. And now I'm computing the cost with this initial theta values. I've randomly initialized and computing the cost, right? And then I'm just calling the gradient descent approach by passing this initial theta, learning rate, and number of iterations, right? So once I get the gradient descent, once I call the gradient descent, it returns the optimal theta to me and also J history. J history is to see whether it is decreasing, increasing with the number of iterations. So here I've just plotted that J history. As you can see, J history I've plotted here with a red line, and I've just added some titles, labels to it. So we're starting here. So everything is ready now. So we're starting here, loading the data set. So this is the function that we have implemented, which returns x and y to me. Once I get x, I'm normalizing x. Okay. And then I'm just adding stack of ones, because the first column should be a column of ones, right? Column vector of ones. I'm just adding that stack of ones here, then dividing the data into training and testing by calling train test split. The test size, I have mentioned it to be 0.3. It means 30% of the data is test, 70% of the data is training. And I'm calling linear regression model, which I have implemented by call on the X train and Y train. Okay, it means I'm building the model based on the training data. I'm not using the test data. So once I get the optimal theta, I'm using it to predict for the test data. I'm just multiplying X test and optimal theta. X times theta will give me prediction, right? So Y theta, Y prediction I have got here. So once I get the Y prediction, I'm calling MAE, which is the mean absolute error, mean absolute difference between Y test and Y predict I'm taking, and I'm just printing this MAE error. The total number of samples is 506, initial cost is 308, and you can see this is how the J value is varying. It is constantly decreasing. It means our gradient descent is working. And the final MAE is 3.18. So the same implementation I've done using the library function. So to do it from the library function, there is a library function called linear regression from sklearn.linear model. So you can directly import this. Similarly, you need not implement MAE. You can directly import it from sklearn.metrics. Okay, so we have also implemented normalization. No, you need not implement normalization also. You can just set normalize equivalent to true here. Okay, I'll show you that anyhow. So the data set I've loaded. I prepared the data set here, X and Y, and I divided the data set into training and testing. And then I've called the linear regression model. So once I get the linear regression model, I'm just fitting it to the training data. So just remember, this pattern is very common. Loading data set, preparing the data set, dividing the data set into training and testing, then calling the model, fitting the model to the training data, and predicting for the test data. So any model you take, this pattern is common. Only thing that will change is the model that you are importing. Okay, so remember this. So the linear regression model, and I'm fitting this model to the training data and predicting for the test data. And the metrics also I've not implemented here. I've just directly imported from sklearn.metrics. You need not implement, it is already there. Various metrics are there. Metrics for regression, metrics for classification, metrics for clustering. Everything is there in sklearn.metrics. You can just explore that. Right. So I'm just printing that MAE and I'm just comparing our implementation with the sklearn implementation. So our implementation gives 3.18 MAE and sklearn implementation 3.16. Means we are pretty much close to that implementation. Means we have done a good job on this. Right. So if you want to visualize this graphically, I'll just show you that Sorry. Okay, so I didn't execute any of this. Let me quickly execute. So you can see this, right? So make regression, you can make your own data sets also, like regression data set, you can make regression you can call. And I'm just generating 2000 samples with the number of features as 1, noise as 15. More noise means more spread. I'm just scattering them. I just fit the linear regression model to this data, and this is how it is looking like. Okay, I'll share this code with you and see. So normalize also need not do. I mean, you need not explicitly implement it. For the linear regression model, you can just pass normalize equivalent to true. It automatically normalizes the data. You need not explicitly do that. Okay, so that's all. If you have any queries, I'll take. Otherwise, we can wind up. Any query?
Again, I have same question I asked in the first day. I have a data set of different air pollutants, for example, carbon dioxide, carbon monoxide, NOx, everything, for 2 years, hourly data. So it's thousands of rows. And for that kind of data, I have to predict in near future each of those pollutants, how much is going
Your
to be
attributes are categorical values or numerical values?
they are all numerical values.
Then you can directly apply linear regression. I mean, any kind of regression. If you think that there is a linear relationship between the input and output variables, you can go ahead for the linear regression. But if not, then the other regression techniques are there that we are going to discuss in the coming sessions.
Yeah.
Yeah. You just simply load your data and apply some regression model.
And do I have to also understand in the model, define the model? For example, the formula that we used, that you explained in the earlier model, without using the
Sorry?
library.
Yeah, you can use the library.
Okay.
So you want to see how the data set looks like? Let me show you that now. Where is this? Okay. There is no attribute yet. Okay. Okay, so this doesn't have it. Okay, let me show you that. You can just print it here. Hey, All right. Right, this is the house price prediction, housing prices, and these are the attributes.
So how do we make it? Now this is all in a not really understandable form to how the prices are going to be.